So welcome to join solid state physics and the chapter 3 we have on the pipeline. So as you can see, we're progressing steadily on the TOC of our course. And this week we'll be focusing really on the mechanical properties of solids. And why I played that earlier instrument, I just wanted to show that we can actually connect this seemingly dull and boring topic of mechanical properties of solids. Also something very cool, for example, music and musical instruments and the acoustic vibrations that take place in such instruments. So maybe that provides you a good kind of other motivation and introduction to this topic we will be covering this week. And what I will do first, we have roughly 4 different topics that we'll be covering that concerns mechanical properties of solids. I will start with this lecture, and this is the introduction and motivation lecture on the topic. So we will basically very quickly define the most important quantities that we will be using, mainly stress, strain, and shear stress will be mentioned. And then after that, we will start heading to the main curriculum, so that we will be focusing on the stress strain curve, and I will be showing you what that is. And then we will be looking at the different regions of the stress strain curve. And then we will be looking from this point of view, what are then the subsequent material properties, the related and then the important material properties. And then on the other hand, how we can connect those macroscopic properties of solids with the microscopic properties of solids. And that's really the focus we have on this course. We want to understand how materials emerge and how they behave, and we want to understand that how we can form this understanding based on the microscopic picture. So we build from this more like a ab initio approach to understand macroscopic solids. So I will now go to the actual part of this lecture. So I will try to motivate why on earth we are interested in the mechanical properties in general in the first place. So what we will do here in this in this chapter 2 is that we want to describe macroscopic behavior of solids, and we want to understand basically what happens when these macroscopic solids are under external forces. So applied stress, shear forces, or for example hydrostatic pressure giving rise to dilatation of a material. So this is what we will be looking into, how a material is being deformed and how exactly it's being deformed when it's under different kind of forces, and what are the microscopic origins of those changes. For simplicity, and this is a very good assumption to make, we will only restrict our treatment to isotropic materials. This is an okay assumption to make when we are dealing with metals. It's pretty bad when we are dealing with graphite. Well, it's actually very bad when we are dealing with materials such as graphite, because graphite, on one hand, it's a accumulation of many graphene layers. And the single graphene layer, as we remember, the atoms are connected via sp2 bonds. And those covalent bonds are very strong, and they give rise to this quite strong graphene layer structure. And then in graphite, we were stacking many graphene layers on top of each other. And these different graphene layers, they are bonded together by a lot weaker van der Waals forces. And it is this difference in the types of forces and the bonding types, so covalent bonds versus van der Waals bonds, that then gives rise to this huge anisotropy in the mechanical properties of graphite. So it's very strong in one direction, and along another direction it's very weak, and especially when we're shearing a graphite, then it breaks loose, it breaks down very easily. But here, for simplicity, we do not consider anisotropic materials, so we only are interested in materials that their response is the same in each direction we are looking at. So this is the assumption we make. And why do we do this? Is that we can then use scalars in our treatment, and we do not need to resort to tensors and vectors. And trust me that if we would really do things properly, we would actually end up with quite tedious tensor algebra that should be used to describe the stress and strains of the materials. So we know the forces that we're applying. A force, it's a vector quantity. So we can imagine that we have three different directions we can apply with the force. So that gives us a vector. And then we have different kinds of strains. And then somehow we need material properties that are connecting strains and with these forces. And then we end up with tensors. So just normal matrices are not adequate anymore in the description of these deformations. So things become mathematically somewhat cumbersome, non-trivial, if we would not assume that we are dealing with isotropic materials. But if you're interested, I think Kittle's book is describing these mathematics I mentioned, and for sure in Wikipedia you can find that if you Google stress tensor and you go to the according Wikipedia page or somewhere else, you will see what I try to tell you here in this lecture. And then to the actual motivation. So why do we care about these properties? Is that in fact, when we look in different fields of science, especially when we look at the material science and engineering, and not into we're not focusing on physics only here, but we would want to apply physics somewhere so that we could actually benefit mankind. And when a solid state physicist is looking for a colleague with whom the person could be collaborating with, then very quickly we end up working together with material scientists and engineers, because they have real issues that they want to solve. They have real problems that they are facing with their materials and systems, and they want to understand how they can solve these problems. And quite often they're actually quite big in caliber, so that they very quickly we end up actually making a difference in the world when we're actually trying to take use of physics, apply physics and solid state physics in material science and in the engineering sciences. So that's why I think this is good to keep in mind, so that they just don't be fooled by the fact that this doesn't seem like a solid state physics chapter, but this really is. But maybe you need to go more deeper into solid state physics, that you start appreciating that ultimately it's about the applications that matter. At some point, we need to go beyond quantum mechanics, and then we actually need to apply what we've learned out of materials, solids. So we really look at these macroscopic properties on this chapter, and they are really important in different fields of sciences. Some examples, for example, what about the durability of materials? Can we make durable materials? This is a valid point. How could we improve things? And is it cost effective if we would make some changes? Aging of polymers, that's also a very big engineering and materials problem right now, that how can we make more longer lasting polymers? And then on the other hand, can we break down polymers more easily so that they could be, we could eradicate them in a more sustainable manners. Then, this is a classic example, resistance to fatigue. So what happens, for example, to metals when they are being bent, and these shearing forces and stresses that are being applied upon a piece of metal, how long the metal can sustain these kind of gradual repetitive stress, and at some point it will break down. And then if the thing that is breaking down is, for example, a massive cruise ship on an ocean with actual passengers inside, then we are speaking of important things here. So that these are some prime examples that we can imagine that are somehow related to this chapter 3. Okay, let's get forward. So what we have here, I will first just define the main properties or forces that we will be dealing with in chapter 3. And then we will outline the general behavioral solids, what happens to them when they are under external forces. So when we apply a stress, what happens? Well, the material is being strained, and then like when we make it systematically, we are actually performing tensile testing so that we are kind of trying to stretch the material, and then we are measuring accurately how much the material stretches. And then we find out that there are actually different regions when we repeat these kind of experiments, and this is the logic and approach we will be using in this chapter. But more of that later. And then we will introduce some material parameters, mainly the elastic constants, and then we will introduce approaches that can be then used with these elastic constants to describe the responses of materials. So elastic constants, that's when the deformations are still repeatable, so that the object returns to its original shape and size after the applied stress has been reduced to zero. And then those are the elastic constants. That's the regime where we want to apply or can apply elastic constants to understand the properties of materials. And this is what we will be introducing next in the upcoming lectures. And after these, we will go and try our best to link these macroscopic properties with the microscopic treatment of solids. And our focus here, what we want to do with this is that we want to provide you a deeper physical understanding of the macroscopic properties. So that hopefully you could understand when you see, for example, a deformation of a solid in real life, and then maybe you can appreciate that, okay, actually something quite interesting happens also in the microscopic point of view. Just an example from real life, the next time you open up a can of butter or the box of butter container, and you have this aluminum foil on top of that, and you know that you can tilt and twist and bend this aluminum foil quite a bit, but nevertheless it doesn't really break up that easily. So the foil, even though it's made of metal, it's quite ductile and it's not brittle. And you could compare, for example, if you would have a kind of thin piece of glass, like a cover slip, or or in a bigger scale, a glass window. You know that if you start bending a piece of a glass, it's not ductile material. It will break up miserably when you start bending it up. So these are some examples that you know, just that what will happen based on your intuition and the kind of real life experiences. So this is what we want to do. We want to kind of somehow remind you that in the end, behind these macroscopic properties and the macroscopic properties we see with our own very eyes, with many different kinds of systems, there's also always this microscopic picture underneath. And hopefully after this chapter, you have a little bit better understanding of these different aspects that play a role. And hopefully you start connecting yourself when you see something interesting the next time. Okay, how come this could be understood based on the kind of microscopic properties of materials? But let's start now by defining applied stress. So what is this? And please memorize what is stress and what is strain on this course. This is important because otherwise, well, first of all, it will be very hard for you to understand what's happening on this chapter 3, but also in the future, this is a bit of terminology that is being repeated, and this is very basic, very fundamental. So it's better that you know the terminology right. So applied stress on a solid that we apply, this is defined with sigma symbol, and the equation that we define is that we have a force F, and that force is being applied in a given cross-sectional area of a solid. So A is the cross-sectional area perpendicular to the applied force. So F is a force, and A is the area perpendicular to the force of the solid. So this is shown in the figure. This is what happens. And the applied stress is defined via this relation. And as you can see, like I already mentioned, that here we're happily dealing with scalars, but of course, like we could very easily replace this force with a vector quantity, and then hell would break loose in terms of the definitions, because then the stresses would also be at least vector quantities, and in some cases even more complicated. Ouch. A note on the terminology. If we have a force that pushes the solid inwards, then we speak of a compressive stress. This makes sense. For sure, it will be compressing the material. And then if the force that we apply, it pulls the solid outwards, then we speak of a tensile stress. And this might be something that the terminology is not that often used in real life. So please remember, like, what is a tensile stress? What is the meaning of that? So that then we're really trying to stretch the material. And this is the type of force that we are applying. Maybe this is not that commonly applied in materials, but especially in this chapter, we will be performing tensile testing. And there, what we are doing to the material that we are looking into is basically that we are applying a tensile stress on the piece of a material. We want to see how it responds. Okay, so then what happens when we do apply the stress? And then what happens is that this solid under question, it will deform, obviously. And this deformation is defined as the strain, and it's called the strain. And epsilon is the symbol we're using. And essentially, strain is defined as the relative change of the length of the solid. So like this is the simplest definition we can find for strain of a material. So we have the delta L, the relative change of the length. So that's just the length change of the material, and then divided by L so that we get the relative length change of the solid. And now again, hell sometimes breaks loose when we are applying a force and we are interested, for example, in a strain that is not along that direction of the force. Solid can also be strained in different directions that are not parallel to the applied stress. So in more general, we should define strain as a vector quantity, so that the epsilon I would be the strain in question, and then we would have a relative change of a material in that given direction. And here, terminology goes such a way that when we have the index I equals to 1, then the strain has a sub-label of 1, and then this is the strain that is parallel to the direction of the applied force. And then we have epsilon 2 and epsilon 3, and these are then the so-called transverse strains, and then in this case, the strain is not along the force. So essentially, for example, while I'm looking at this figure, we are performing we are applying a tensile stress on our piece of a material, and then when we are also wanting to understand how its other directions change, so how the other dimensions of the material get changed, then we should quantify these changes with the transverse strains, so epsilon 2 and epsilon 3. Okay, and then we can have even different types of stresses depending on how many forces we have, and are we then, for example, perpendicular with respect to the cross-sectional area A, or are we parallel? So let's go first through the compressive forces and compressive strain. So solids often contract when they are under a compressive stress. And this is what happens in the picture. Now I will have the picture, so that when we press a material, it compresses along this direction, but the other directions usually it bulbs out, so that it actually expands in these other directions. So this is what happens. And in addition to this, that the other directions, or let me start again. Now let's consider a case that we have a force that is not just perpendicular to the surface A. That's what it says on the slide. But we actually may have also a parallel force. And this force then will give rise to a new type of stress, and we call that shear stress. And this is shown in the figure, so that the scenario looks then like this, so that we have the cross-sectional area of our solid, and now we are actually applying the force sideways. And subsequently, when we would define that what is actual amount of stress we are now imposing into the material, then we should actually now calculate the surface area and the force, and then we would get the shear stress. And this is also quantified how much do we deform the material. Instead of strain, we are often using deformation angle alpha subsequently as a way to tell how much the solid is being deformed due to application of shear stress. And finally, we consider a uniform force, or stress that deforms the solid. And how this could be happening, well, for example, we could be placing the solid under water or a liquid, and then we would have a hydrostatic pressure on the solid. Well, of course, we also have similar pressure already in the atmosphere. So this is actually always present, this hydrostatic pressure, and it's actually not minuscule. It's not very small on Earth, but we just don't feel it ourselves, because our human bodies, for example, are used to this pressure that we have pressing us on all directions. So these are the kind of different stresses that we can have, and then subsequently the object will be deformed, and this is what we will be covering in this chapter in a nutshell. So I thank you for listening of this introduction video, and next we will go into the stress strain curve, and we will go through these concepts in more detail, and we will learn more about the types of deformations that will happen, and what are the main characteristics we should know about these deformations and forces. So I thank you for listening, and please stay tuned, and we will meet again soon regarding the course and lectures. Bye.